From the molten breath of a newborn world to the rhythmic pulse of ice and sunlight, Earth's climate has never simply been, it has always evolved. Hello there, and welcome to the Late Night Scientist channel. In this journey, we'll drift through deep time to watch oceans rise, continents wander, forests rewrite the sky, and life itself reshape the air. Settle in, let your thoughts soften, and follow the long, unbroken story of how our planet learned to balance warmth and cold, not by settling down, but by learning how to keep going. In the beginning, long before continents drifted, before oceans hushed their weight onto the surface, before even the quiet chemistry of life, there was heat. Endless, unrestrained heat, the kind that blurred the boundary between rock and flame. The young Earth had only just assembled itself from a swirling disk of cosmic leftovers, each fragment drawn inward by gravity's patient tug. But that assembly did not come with a user manual. The result was a planet still trembling from its own creation, glowing with internal fire, wrapped in an atmosphere far too thick and violent to resemble anything we know today. This early world was not a place of gentle breezes or calm twilight. Its climate, if one could generously use that word, was more of an ongoing identity crisis involving molten plains, constant bombardment, and a temperature scale that humans would politely decline to experience. Magma surged across the surface like slow-moving oceans of orange and red, each wave carrying the memory of the planet's collisions. These collisions were not mild introductions. They were catastrophic slams from wandering protoplanets and asteroids, each one adding heat rather than giving Earth the space to cool. The energy of impact vaporized rock, launched debris back into orbit, and thickened the skies with choking clouds of silicates and metal-rich vapors. This was not yet a world with weather. There were no clouds drifting thoughtfully across the sky, only plumes of incandescent dust hurled upward by the next impact. Lava fountains burst through the crust with the enthusiasm of a planet learning how to breathe, releasing steam and gases that pooled into an atmosphere dense enough to trap the heat radiating from the still molten surface. Earth seemed determined to try every extreme temperature at least once, as if auditioning for a cosmic role it hadn't quite decided on. Gravity, always the quiet sculptor, worked to round the planet, settle the debris, and pull heavier materials toward the core. Deep below the chaotic surface, iron and nickel sank inward, forming the metallic heart that would one day anchor Earth's magnetic field. But here at the surface, the story was still uncomfortably warm. The crust wobbled in and out of solidity, sometimes hardening just long enough to crack and sink again into the molten mantle. If one had stood upon this trembling ground, not that anyone would volunteer, the land beneath would feel unstable, like stepping on cooling wax. Even in this turmoil, patterns began to form. Volcanic ridges stitched themselves across the surface, releasing torrents of gas that thickened the early atmosphere. This atmosphere was not yet protective. It behaved more like a thermal blanket you'd refuse politely in a well-heated room. The sun, dimmer than it is today, but still vigilant, shone faintly through the haze, its light scattering off particles that glowed in an eerie copper red. But sunlight barely mattered. Earth's surface heat outshone the sky, rising from the ground in shimmering waves. Meteorites continued to rain down, bringing with them minerals from distant parts of the young solar system. Some held water locked in crystals, but here that water instantly vaporized, entering the atmosphere as fleeting wisps of steam. The impacts stirred the molten rock below, preventing the crust from settling into anything permanent. Each collision reset the planet's progress toward stability. It was evolution at the scale of worlds, slow, violent, and strangely deliberate. Amid all this chaos, Earth was cooling, just very, very slowly. Space siphoned off the excess heat, though the atmosphere did its best to trap it, and the molten oceans gradually thickened. The first true crust began forming, fragile and cracked, like the skin that cools atop boiling soup. Lava still fractured it from below, but for the first time, something resembling a surface existed. And with this surface came the first hints of what would eventually become climate regulation. The balance between heat leaving the planet and heat being held in by the atmosphere. It was crude, messy, and inconsistent, but it was a beginning. Thunder did not yet rumble here, nor did rain fall. Winds were barely a concept. Instead, Earth's early atmosphere roiled with convection, hot gases rising and swirling as cooler ones descended, creating slow, churning movements that sculpted the fiery sky. If one could drift above it all, they might see a planet trying to settle into itself, every plume of lava and every new crater part of its long attempt at balance. And while Earth was certainly not comfortable, it was determined, radiating an energy that suggested it would eventually figure things out. Occasionally, in the rare lull between impacts, the molten plains glowed steadily, uninterrupted by falling stone. In those moments, Earth almost seemed peaceful, like a restless creature finally pausing for breath. But the stillness never lasted long. Another meteorite would blaze through the atmosphere, splitting the sky with a white-hot streak and reminding the planet that youth is rarely calm. Yet even this chaos held purpose. Each impact heated the planet, but also helped mix its layers. Each volcanic eruption thickened the atmosphere, but also released gases that would eventually support water and weather. Every action, though violent, was part of the long sculpting that would turn this raw, molten sphere into a world capable of climate, oceans, continents, and eventually life. For now, though, Earth remained in its fiery infancy, brilliant, unstable, and loudly alive, still trying out extreme temperatures before deciding which direction it might want to head next. The newly cooling Earth wore its earliest sky not as a delicate veil, but as a dense, mineral-stained shroud, a sky that seemed carved from stone rather than painted with light. It was a world where the concept of blue had yet to be invented, where the air was a heavy mixture of volcanic breath, thick with uninviting gases that clung to the planet like a second crust. This was an atmosphere in the making, shaped not by wind or weather, but by the deep rumblings of a world still settling into its planetary identity. Volcanoes were the architects of these first skies, They towered in jagged rows across the surface, venting gases from Earth's interior with tireless persistence. Each eruption expelled clouds of carbon dioxide, methane, sulfur dioxide, and water vapor, gases that drifted upward to accumulate in the cooling air. There were no plants to absorb carbon dioxide, no oceans deep enough yet to hide it, and no living chemistry to recycle anything. The gases simply built layer upon layer, forming an atmosphere so dense it carried the weight of the world's fiery origins. Had there been anyone watching at the time, they would have seen a landscape ruled by rising plumes of gas, each eruption adding another stroke to the sky's somber palette. The haze was so thick that sunlight arrived diffused and weakened, scattering in amber tones through the particulate-choked air. Day was more of a suggestion than a clear event. Light entered the atmosphere only to be softened, bent, and swallowed by the suspended dust and droplets drifting endlessly above the molten surface. This primitive sky had no oxygen to speak of. The idea of breathable air was still far in the future, tucked away in the countless chemical steps evolution had not yet begun to take. Instead, the air felt sharp, metallic, and stinging, its sulfur and methane content creating an aroma that would make even the hardiest modern traveler politely reconsider their vacation plans. Yet for Earth, this atmosphere was more than a smelly inconvenience. It was the first attempt at climate control, a natural greenhouse blanket capable of trapping heat radiating upward from the molten plains. Weather, as we know it, simply did not exist. There were no clouds shaped by gentle currents, no raindrops, no winds rustling across any surface. Instead, the atmosphere churned in great, slow-moving convection cells, heated from below by the glowing crust and cooled only slightly at higher altitudes. Hot gases rose in thick columns, stretching upward until they lost some of their thermal energy and drifted outward, eventually sinking again. These motions were heavy and lumbering, like the breath of a creature half asleep but still trying to regulate its temperature. Even with sunlight dimmed, Earth's interior heat supplied most of the energy shaping the early climate. The planet radiated warmth like a stove just turned off, still far too hot to touch, still glowing in places, but gradually losing energy to space. The atmosphere trapped enough of this heat to prevent the surface from cooling too quickly, creating a feedback loop. Warm ground heated the atmosphere, and the atmosphere, in turn, slowed the loss of warmth back into the surrounding darkness of space. Over time, as volcanic activity remained relentless, water vapor began to accumulate in the sky. It drifted in thick, invisible swaths rather than forming clouds. The planet was far too hot for condensation. Water could only exist as gas, swirling with the carbon dioxide and methane. The air held this vapor like a promise of future oceans, waiting for a cooler world to give it form. What made this early atmosphere remarkable was its density. It pressed down on the surface with a force modern Earth no longer remembers. Every gas molecule contributed to the heavy cloak resting over the planet, thick enough to blur the horizon and swallow sunlight in its depths. And yet, despite its weight, This atmosphere offered no comfort. It insulated Earth, but it did nothing to stabilize temperatures or spread heat gently across the surface. Instead, it created pockets of intense warmth where heat became trapped, swirling around volcanic vents and lingering over cooling lava fields. Slowly, the balance began to shift. The crust thickened, the impacts grew fewer, and the most violent eruptions gave way to steadier volcanic breathing. With each passing millennium, the atmosphere grew more defined. Carbon dioxide levels fluctuated as some gases settled into the crust, while others escaped into the air. Methane added an extra layer of temperature sensitivity, amplifying the greenhouse effect. Sulfur dioxide formed droplets that reflected the faint sunlight, tinting the sky with murky hues and softening the stifling glow from the surface. Through this process, Earth's atmosphere transformed from raw, outgassed fumes into something more nuanced, still toxic, still intense, but increasingly capable of influencing climate rather than simply recording the planet's volcanic moods. It learned, in a geologic sense, how to trap enough heat to keep the surface warm without instantly boiling every molecule of water or metal that dared appear there. It was as if the sky was slowly teaching itself moderation. No oxygen yet drifted through this air. No comforting ozone shield filtered the ultraviolet light pouring from the young sun. But the atmosphere had formed, and with it came the earliest whispers of climate as a tool, one the planet would refine across billions of years. For now, it remained a stony sky, thick with the signature of volcanoes, heavy with the breath of a world still cooling from creation. Earth was learning, step by step, how to wear its air. Once Earth's surface finally began to ease away from its molten frenzy, the change did not arrive with a dramatic snap, but with a slow, cooling sigh. The seething crust, once too unstable to hold anything for long, thickened into broader plates that could survive more than a few geological moments before giving way. Lava still pulsed beneath the surface, but the world was no longer glowing from every direction. It was, in an almost reluctant gesture, beginning to cool. And with cooling came the first great turning point in the planet's climate: the arrival of rain. Not the passing showers we know today, nor even the towering storms that shake modern coastlines. This was rain on a scale beyond imagination. Rain that began timidly, then gathered momentum, falling in sheets that thickened into torrents, then softened again into steady, ceaseless drizzle. It was as though the sky had been holding back a great breath and finally released it, drop by drop, in a process that lasted millions of years. If Earth had discovered the off switch on its lava, then this rain was its victory dance, long, unhurried, and very, very wet. At first, the drops evaporated as soon as they touched the still hot crust, vanishing in tiny clouds of steam that rose with quiet determination. But the crust persisted in cooling, radiating its leftover heat into space at a pace that even the thick, heavy atmosphere could not entirely counter. Eventually, some raindrops survived, splashing against rock that had hardened enough to hold their weight. The water hissed on contact, spreading across the ground in thin trickles that darted between cracks and fissures like explorers mapping new territory. These small rivulets evaporated quickly, but they were a promise of something larger. As the world cooled further, rain shifted from ephemeral to relentless. The steam that once leapt skyward now hung in the air, thickening clouds and feeding a cycle of condensation that grew stronger with every passing millennium. Entire regions were draped in mist so profound that sunlight had to negotiate before reaching the surface. Storm systems built themselves out of the dense atmosphere, not in tight spirals but in sprawling, sluggish masses that lumbered across the landscape, shedding torrents of mineral-rich water. Every drop that reached the ground carried with it the blueprint for oceans. Water pooled in the planet's lowest basins, collecting in shallow depressions formed by ancient impacts and early crustal warping. These basins began as puddles, then lakes, then inland seas, gradually merging into wider expanses. And as they spread, they carved new channels, shaping the still soft crust, smoothing jagged slopes and carrying sediments toward deeper waters. The first waves lapped against shores made of black volcanic rock, unwitnessed and unhurried. The rain did not simply fill the oceans, it also altered the atmosphere above. With every deluge, gases dissolved into the water, removing some of the heavy burden from the sky. Carbon dioxide, once content to linger in the air, found itself drawn into solution, quietly shifting into new forms that sank toward the seafloor. Sulfur compounds followed, settling into the deepening ocean as the water performed its first great act of climate regulation. This was not yet a balanced system, but it was the beginning of one. The sky, stripped of some of its density, grew marginally clearer. The horizon sharpened. Sunlight reached the surface with fewer obstacles. Meanwhile, the oceans warmed from below. Heat still rose through the crust, raising the temperature of the accumulating waters and filling them with dissolved minerals. These early seas were far from the familiar blues of today. They shimmered with metallic hues, tinted by iron and silica, their surfaces often veiled in mist from the still warm ground. But they were oceans nonetheless, vast, patient, and ready to reshape Earth's climate in ways the planet could not yet imagine. Rainfall sculpted more than just basins. It weathered the surface, breaking down rocks into fine sediments that washed into the expanding oceans. This slow erosion changed the chemistry of the waters, stirring new reactions that further adjusted what the atmosphere could hold. Weathering also cooled the crust faster. Each raindrop carried away a tiny fraction of heat. Multiply that by millions of years of uninterrupted rainfall, and the cooling effect became profound. Earth's surface finally stabilized enough for large regions of solid land to endure. This stabilization changed the rain itself. Storms became more structured, shaped by the contours of new landscapes. Valleys that funneled wind, ridges that lifted clouds upward and wrung them dry. The cycling of water between sky and surface grew more complex, developing early rhythms not yet governed by seasons, but by thermal contrasts between rock and sea. In this young climate, the oceans acted as vast heat sinks, slowing temperature swings and regulating the atmosphere's energy. Thunder began to rumble in those dense, mineral-rich skies. Lightning flickered across the horizon, illuminating landscapes still cooling from their molten past. The storms fed themselves on the heat rising from the crust, discharging energy in bright, sharp bursts. Each bolt hinted at chemistry beginning to stir, reactions that would one day, much later, nudge life into existence. But for now, the lightning simply echoed across the ocean basins, a bright punctuation in a world still settling into its cooler identity. Perhaps the most astonishing aspect of this time was its patience. The rain did not rush. The oceans did not form overnight. Everything unfolded with the slow, deliberate pace of geology, a process uninterested in haste, content to sculpt a stable world drop by drop. Earth, once blazing and chaotic, now entered its long, watery chapter, guided by the steady fall of rain that seemed determined to turn the entire surface into a reflective, shimmering cradle of future possibility. By the time the rains finally eased, after millions of years of patient work, Earth had changed completely. Where once lava seas glowed, oceans now stretched in wide, quiet sheets. Where volcanic haze once choked the atmosphere, clearer skies now allowed more sunlight to reach the surface. And in the soft roar of these newborn seas, the planet found its first true climate stabilizer, a partner in the long, unfolding story of its evolution. Earth had cooled, reshaped, and learned to hold water. It was ready, at last, for the next chapter. With oceans now spreading their reflective surfaces across the planet, and the crust finally cooled enough to hold firm land masses for more than a fleeting moment, Earth entered a quieter, but no less precarious, phase of its climatic education. Above, the sun shone with a gentleness that seems almost unbelievable today. It was a younger, leaner version of itself, radiating only about 70% of the brightness it would one day command. Had Earth relied solely on this faint sunlight, the oceans that had so patiently formed might have frozen into solid shells, locking the planet in a deep slumber long before life had the chance to stir. Yet Earth remained warm enough for liquid water to persist. It was a thermal puzzle. How could a dim sun illuminate a world that refused to freeze? A paradox whispered across the ages by geologists and astronomers, one that the planet itself solved long before anyone ever named it. The answer came from the air, that thick, evolving sky that had grown outgassed, storm-washed, and slowly clarified. Though the atmosphere had lost some of its early heaviness, it still retained a generous supply of heat-trapping gases, forming a blanket that held warmth close to the surface. These greenhouse gases, primarily carbon dioxide and methane, were not decorations in the air, but the planet's first climate negotiators. Sunlight entered the atmosphere as visible rays, warming the ground and oceans, which then radiated that energy back upward as infrared heat. Instead of escaping into the cold vacuum of space, much of this infrared energy was intercepted by the greenhouse molecules, absorbed, and gently re-emitted. The effect was not unlike layering warm blankets over a cooling body, subtle, consistent, and life-preserving. Earth, still young and eager, discovered that even a shy sun could sustain warmth if the air knew how to hold it properly. The atmosphere, having shed some of its earlier volcanic burden, had grown more nuanced. The haze had thinned enough to allow more sunlight to touch the surface, but still remained dense enough to trap outgoing heat. This produced a delicate balance. Too much atmospheric density, and Earth risked overheating under its own insulation. Too little, and the oceans might begin to freeze from the poles downward. But the planet seemed to thrive in this narrow path, adjusting its atmospheric chemistry through the slow processes of weathering, outgassing, and ocean atmosphere exchanges. Meanwhile, the sun, still in its youthful stage, was slowly increasing its energy output. This wasn't a sudden shift, but a quiet, incremental brightening that unfolded over hundreds of millions of years. If the sun could speak, it might have apologized for its earlier shyness, explaining it was simply growing into its role. But Earth did not wait for the star to mature. It crafted climate solutions of its own. Thick greenhouse gases acted as the planetary equivalent of warm clothing, preventing catastrophic cooling while the sun took its time warming up. Earth's climate, for the first time, displayed signs of negotiation, an almost conversational relationship between the energy arriving from space and the atmospheric layers deciding how much should be retained. In this era, climate wasn't a fixed outcome but a balancing act unfolding slowly and thoughtfully, shaped by feedbacks that took millennia to register. The oceans absorbed heat by day and released it by night, smoothing out temperature swings. The atmosphere trapped warmth with exquisite patience, offering stability where none should have existed. Yet this balance was fragile. A slight change in volcanic activity could alter the concentration of greenhouse gases. A shift in cloud cover, still rudimentary, newly forming from the evaporation of warm oceans, could brighten or dim the amount of sunlight reaching the ground. Even the composition of minerals forming on land played a role. Certain rocks weathered more quickly, pulling carbon dioxide out of the atmosphere faster than others, and briefly cooling the world until volcanic outgassing replenished it. Earth, in its quiet way, experimented. Sometimes it tipped toward warmth, as increased volcanic activity fortified the atmospheric blanket. Other times, it teetered toward chilliness, as weathering and rainfall redirected gases into oceans and rocks. But just when it seemed the planet might slide too far one way or the other, internal feedbacks nudged it back toward equilibrium. The oceans, vast and patient, absorbed excess heat when the world grew too warm and released it slowly when the sun dimmed behind thicker clouds. In these long stretches of experimentation, Earth became a master negotiator, maintaining conditions suitable for liquid water under what should have been a frigid sky. This chapter of its story is not marked by dramatic scenery or explosive transformations, but by the quiet triumph of balance, the moment when the planet learned to regulate itself with atmospheric precision. It was during this time that Earth discovered an almost shy resilience. The sun grew brighter at a glacial pace, raising the planet's temperature bit by bit. But the atmosphere responded in kind, adjusting greenhouse levels through slow chemical cycles. This equilibrium was not perfect, nor was it permanent. but it was enough. Enough to keep the oceans from crystallizing. Enough to allow continents to form more steadily. Enough to prepare the stage for all the climatic dramas yet to come. And though the Earth of this era was not bustling with life, nor adorned with green landscapes, it carried within its atmosphere the early promise of both. The climate learned moderation, not through intent, but through countless interactions between rock, water, air, and sunlight. It was as though the planet gently tested each variable, adjusting the balance until warmth and coolness held hands across geological time. The sun would continue to brighten, and Earth would continue to negotiate. But in this early moment, the planet had achieved something remarkable. Under a faint star, with oceans still new and landscapes raw, it held on to warmth through ingenuity encoded in chemistry and physics. Climate had begun its long conversation with the cosmos, one that would change with every chapter the planet lived through. For hundreds of millions of years, Earth's climate had been governed by forces large enough to reshape continents and deep enough to stir molten rock. Volcanoes sculpted the air, oceans moderated the heat, and sunlight, still gathering strength, provided the rhythm by which the planet warmed and cooled. It was a world ruled by geology and physics alone, a quiet interplay of stone, water, and sky. But then, almost imperceptibly at first, small clusters of greenish film began coating the sunlit shallows of Earth's early seas. They were tiny, fragile, and easy to overlook. Yet these unassuming organisms would become some of the most influential climate engineers the planet would ever know. They were cyanobacteria, photosynthesizers of astonishing efficiency and even greater patience. These microscopic architects drifted in calm waters, forming mats that fluttered with the movement of waves. They had no bones, no complex structures, no idea that they were about to alter the fate of the planet. All they possessed was a type of molecular machinery that could capture sunlight, split water, and use that energy to build organic matter. It was a process so elegant and so transformative that its consequences would ripple across billions of years. Before this moment, Earth's atmosphere was dominated by carbon dioxide, methane, and traces of other gases born from the restless interior. Carbon circulated between the sea and the sky, but there was no biological hand pushing it in one direction or another. Cyanobacteria introduced a new pathway, quiet but relentless. With every flicker of sunlight, they drew carbon dioxide into their tiny bodies, rearranged it into sugars, and released a waste product that had been largely absent from Earth's air: oxygen. In the beginning, the oxygen had nowhere to go. It reacted eagerly with minerals on the seafloor, binding to iron and other elements in a rush of chemical enthusiasm. The oceans turned rusty in places, as iron-rich sediments absorbed the new gas. But the cyanobacteria didn't stop. They lined the shallows, spread across tidal flats, and formed layered stromatolite mounds that slowly reached upward like microbial stone gardens. Their efforts were tireless, as though sunlight was a challenge they were determined to meet every day. Oxygen seeped into the oceans, then into the air. The atmosphere did not accept this change gracefully. Methane, once abundant, began reacting with oxygen and disappearing. Carbon dioxide levels dipped as biological activity expanded. Gas by gas, the composition of the air shifted, like a room being quietly redecorated without anyone noticing until the furniture had all moved. Earth had invited life in, not realizing it would start redecorating the entire atmosphere. The climate began to respond, slowly at first, then with gathering momentum. Oxygen, unlike the greenhouse gases it replaced, did not trap heat efficiently. As methane levels dropped, the insulating power of the atmosphere weakened. Sunlight still warmed the surface, but more of that warmth now escaped into space. The balance that had kept the seas liquid under a gentle sun began to tip ever so slightly toward cooling. Yet cyanobacteria didn't operate with any grand plan. They were simply doing what their chemistry allowed, floating, growing, dividing, and basking in light. Their activity created oxygen not as a goal, but as a byproduct. They were, without knowing it, rewriting the planet's climate script. Over millions of years, the partial pressure of oxygen in the atmosphere crept upward. It was still minuscule by modern standards, but significant enough to alter the planet's chemistry. As oxygen rose, ozone formed in the upper atmosphere. This thin, delicate shield absorbed ultraviolet radiation, allowing more stable conditions at the surface. For the first time, Earth had an atmospheric layer that protected its water and its potential avenues for life. The oceans, now shielded slightly from harsh solar radiation, grew more stable and complex in their chemical gradients. The calm shallows became laboratories where evolution could experiment with new forms, each tiny innovation interacting subtly with the climate. While oxygen began its slow ascent, carbon continued to be fixed into living material. When these organisms died, they sank to the seafloor, carrying carbon with them. Over unimaginable spans of time, this burial of carbon altered the composition of both the oceans and the air. The atmosphere thinned slightly, cooling in response. It was the first time life had reached out and touched the thermostat, even if it did so with a tiny microbial hand. Climate feedbacks shifted accordingly. Cooler temperatures altered ocean currents, encouraging slow circulations that carried nutrients around the globe. The seabed grew carpeted with sediments rich in organic material, locking away gases that once floated freely in the sky. The air grew clearer, less hazy, and more capable of transmitting sunlight to the surface without scattering it into fiery reflections. The world was far from frozen, but it was changing. The atmosphere that had once been dominated by volcanic breath was now shaped by photosynthetic whispers. Cyanobacteria persisted through storms, through shifting coastlines, through cycles of nutrient scarcity and abundance. Their mats expanded and contracted with the tides, producing oxygen steadily, like tiny factories powered by sunlight. As oxygen continued to rise, it prepared the stage for future transformations, some gentle, others dramatic. But in this chapter of Earth's history, the key shift was not about the extreme impacts that would one day unfold. It was about the quiet, cumulative influence of life's first climate conversation. The planet's atmosphere was no longer solely dictated by stone and heat. It had a new participant, tiny, persistent, and endlessly productive. Earth was no longer just cooling or warming. It was adapting, negotiating, learning to share control of its climate with the smallest inhabitants in its oceans. And from this moment onward, the story of climate would forever be entwined with the story of life. As cyanobacteria continued their patient work beneath the sunlit shallows, the atmosphere steadily shifted toward a new chemical identity. Oxygen, once an inconsequential trace gas, began to accumulate with a persistence that only countless generations of photosynthetic microbes could achieve. It crept upward molecule by molecule, reacting with dissolved iron, then saturating sediments, and finally leaking into the air in amounts too large for the planet's chemistry to quietly absorb. What had begun as a gentle biological whisper was becoming a planetary declaration. But oxygen was more than a new face in the atmosphere. It was a disruptor. Some gases welcomed it politely before reacting away. Others fared far worse. Chief among the casualties was methane, a greenhouse gas vastly more potent at trapping heat than carbon dioxide. Prior to this shift, methane helped maintain a comfortable warmth under a sun that was still dimmer than today. But oxygen and methane are notoriously incompatible roommates. They react quickly, transforming into carbon dioxide and water, leaving far less methane in the atmosphere to keep Earth warm. As this oxygen-methane tug-of-war intensified, the planet's heat budget began to tilt. With methane concentrations falling, Earth's greenhouse blanket thinned dramatically. And unlike CO2, which builds up slowly over long geological stretches, methane responds almost immediately to changes in chemistry. It was as though the atmosphere had misplaced its warmest coat just as the sun was still offering only a lukewarm embrace. The cooling that followed was not gentle. It was sharp, persistent, and startlingly global. Ice began to form in places that had never known freezing before. At high latitudes, snow accumulated faster than it could melt, reflecting sunlight back into space. This icy armor expanded steadily, creeping across coasts and swallowing shorelines. Even at lower latitudes, where warmth typically lingers, the atmosphere's weakened heat-trapping power allowed chillier temperatures to settle. The feedback loop was swift. More ice reflected more sunlight. More sunlight lost meant more cooling, and more cooling invited even greater expanses of white across the continents. For Earth, which had grown accustomed to the humid warmth of an earlier age, this shift felt like a sudden and dramatic climate shock. The planet was not simply cooling, it was transforming. Oceans that had long been stable thermostats responded slowly but unmistakably. Their surfaces cooled, allowing deeper layers of water to overturn, pushing nutrients and dissolved gases through the marine system in unfamiliar patterns. Winds sharpened, driven by new temperature contrasts between icy land masses and chilled seas. The entire climate system seemed to rearrange itself, startled by the consequences of life's biochemical innovations. This was the first time life had meaningfully tugged on the planet's thermal reins. The cyanobacteria, continuing their daylight-driven routines, had no concept of climate engineering, yet their metabolic byproduct triggered a cascade of environmental changes that reached from ocean floors to the outer edges of the atmosphere. Their oxygen transformed the chemistry of minerals, reshaped the balance of greenhouse gases, and redefined how heat flowed around the planet. It was not intentional, but it was profound. As the cooling intensified, glaciers expanded with quiet determination. They grew thick and heavy, pressing against the crust, carving grooves into bedrock, and grinding stone into fine silt beneath them. In some regions, ice sheets spread so broadly that they fused into vast, bright expanses, stretching horizon to horizon. Each snowfall thickened the icy armor. Each passing winter deepened the chill. The planet entered one of its earliest prolonged glacial episodes, a world slowly icing over under a sky newly rich in oxygen. This created a climate feedback unlike anything Earth had experienced. With more ice reflecting sunlight, surface temperatures dropped further, reinforcing the spread of glaciers. At the same time, the newly oxygenated atmosphere allowed ultraviolet radiation to form a thin layer of ozone high above. This shield protected the surface from UV rays, subtly altering how energy entered the climate system. While ozone itself didn't warm the planet much, its presence signaled that atmospheric chemistry had become layered, complex, and capable of influencing climate in multiple ways at once. Despite this icy encroachment, the planet was not entirely frozen. Warmth lingered in certain pockets, regions where volcanic activity continued to vent heat and gases into the atmosphere. Volcanoes, with their deep connection to Earth's mantle, had not paused during this climatic upheaval. Their emissions delivered carbon dioxide back into the sky, offering a slow, persistent counterbalance to the cooling triggered by methane's collapse. Yet volcanic CO2 accumulated far more gradually than oxygen, so its influence was subtle at first, a background whisper against the more immediate chill. The oceans, too, held on to their internal warmth, though their surfaces cooled. Beneath layers of ice and chilly water, currents still circulated, carrying energy around the globe. Chemistry at the ocean-atmosphere boundary shifted dramatically. With oxygen now present, new reactions shaped the composition of seawater. Minerals began to precipitate differently, locking away various elements in new forms. The seafloor recorded these changes in layers of sediment that would someday tell the tale of an atmosphere reinventing itself. As Earth continued to cool, the planet entered a state of climate self-reflection, one in which biological and geological processes intertwined. Life had altered the air. The altered air had changed the temperature. The changed temperature influenced ocean circulation, ice formation, and weather patterns. The feedback loop was clear. Climate and life were no longer separate domains. They shaped each other. They responded to each other. They negotiated the future together, even if the participants were unaware of their roles. Eventually, over millions of years, volcanic emissions accumulated enough carbon dioxide to soften the chill, pushing back against the advancing ice. But during this long stretch of planetary winter, Earth learned something essential. climate could pivot sharply when its atmospheric chemistry changed. A single shift, oxygen rising from countless tiny organisms, had the power to reshape oceans, land, and air. This was the first major climatic shock in Earth's history, a revelation that climate was not a passive backdrop, but an active, dynamic partner in the story of the planet. And it would not be the last time life stepped in to adjust the atmospheric script. There are winters, and then there are winters so determined that they forget the concept of moderation altogether. During one of Earth's most dramatic climatic turns, the planet embraced the latter, entering an icy state so complete, so far-reaching, that even equatorial oceans stiffened beneath thick slabs of frozen surface. It was a moment when the climate seemed to halt mid-breath, as if the entire planet had decided to try out being a cosmic snow globe. In the long arc of geologic time, this era stands out as Earth taking winter a little too seriously, coating itself in ice from pole to pole. The transition did not happen in a single sweeping gesture. Instead, cooling intensified over eons, the world dimming itself through a set of feedbacks that nudged temperatures downward step by step. Once glaciers gained a foothold, they advanced steadily, unfurling across continents like quiet, unstoppable armies of frozen white. The more they spread, the more sunlight they bounced back into space. Ice is a master reflector, and Earth, now covered in gleaming expanses, lost precious warmth as solar energy ricocheted off its surface. This ice albedo feedback deepened the chill, encouraging glaciers to stretch farther still. Even the oceans were not exempt. Sea ice thickened across the surface, welding into sheets that drifted outward and fused into vast, continent-spanning platforms. Beneath them, seawater remained liquid, but the interface between ice and ocean grew silent, dim, and insulated from the wind-stirred world above. Light, already softened by distance from the sun, now struggled to penetrate the icy crust. The upper layers of ocean approached stagnation, held in place by the frozen lid that prevented waves from forming or winds from mixing surface waters. The atmosphere cooled to match the surface, its circulation patterns slowing as energy drained from the system. Winds weakened, losing the vigor that once carried moisture and warmth across the globe. With so much of Earth's surface locked beneath ice, evaporation plummeted, and the familiar cycling of water through clouds and rain nearly disappeared. Instead of storms, the world entered a period of eerie stillness. What little weather remained unfolded sluggishly, shaped more by subtle thermal differences than by any lively atmospheric stirrings. On land, what little remained visible, glacial ice towered in thick, uneven slabs. These glaciers were not gentle rivers of ice, but immense, grinding behemoths capable of reshaping entire landscapes. As they crept forward, they scoured bedrock, carving deep grooves and carrying broken stone downward in their slow, relentless crawl. Valleys became over-deepened basins. Mountain flanks vanished beneath flowing walls of frozen blue. Every movement of these glaciers erased old terrain and prepared the canvas for landscapes that would emerge far in the future. Yet beneath all this frozen silence, Earth's interior continued its tireless work. Heat from the mantle rose upward through faults and fractures, circulating through the crust even as the surface lay frigid. Volcanoes, never ones to take long vacations, continued their activity beneath the ice. Their eruptions did not burst into open air. Instead, they released gases into the confined spaces beneath glaciers, carving chambers of warmth beneath the frozen ceiling. Most importantly, these volcanoes exhaled carbon dioxide, adding it slowly but steadily to the atmosphere. At first, this volcanic contribution seemed insignificant. The thickening ice absorbed sunlight with such eagerness that a little added greenhouse gas could not shift the balance. But volcanic CO2 has the patience of a mountain. Over millions of years, without rain to wash it away or vigorous vegetation to absorb it, carbon dioxide accumulated. The atmosphere, once thin and chilled, gradually thickened with this invisible insulation. Each new molecule added a tiny fraction of warmth, barely noticeable in the moment, but monumental across vast geological spans. Deep in the oceans, life endured in pockets warmed by geothermal heat. Hydrothermal vents continued to spew mineral-rich water, sustaining ecosystems in the darkness beneath the ice. These isolated communities persisted, insulated from the frozen world above, continuing their own modest biological routines while the planet around them lay nearly dormant. As CO2 accumulated in the sky, Earth reached a quiet tipping point. The greenhouse effect, now strengthened by countless volcanic exhalations, began to trap a bit more heat. Temperatures inched upward, not enough to melt the ice immediately, but enough to weaken the feedbacks maintaining the global freeze. Eventually, the balance shifted. Sunlight, still reflected vigorously by ice, now met an atmosphere increasingly unwilling to let warmth escape. The planet gathered heat beneath its frozen shell, like a sleeping creature slowly stirring. When melting finally began, it was unhurried but unstoppable. The first cracks appeared as subtle fractures in sea ice, barely noticeable from afar. Then, as warmth built beneath the glaciers, meltwater formed rivers beneath the frozen surface, lubricating the base of the ice sheets and accelerating their retreat. Once sunlight reached darkened land or open patches of water, those areas absorbed heat eagerly, further hastening the melt. The great glaciers began to shrink, withdrawing from their farthest reaches in a slow but monumental reversal. The oceans sighed back into motion as ice retreated. Winds regained strength, redistributing heat and moisture with renewed vigor. Eventually, open waters spread across the equatorial regions, shimmering under a sky transformed by carbon dioxide. Earth had thawed from its global winter, a world that had nearly become a frozen monument to its own climate instability now reawakened into fluid, dynamic motion. Snowball Earth was a reminder that the climate could swing dramatically when pushed by feedbacks at planetary scale. Ice, sunlight, atmosphere, and geology had all conspired to lock the world into cold and then patiently unlock it. The planet emerged altered, its landscapes recarved, its oceans restirred, its atmosphere reshaped by volcanic persistence. Earth had learned, in this deep freeze, that balance is never guaranteed, and that sometimes, Even a planet needs time to thaw out after taking winter far too seriously. When Earth slipped into its near-global freeze, it settled into a stillness so profound that even the atmosphere seemed to pause. The planet's surface lay trapped beneath blankets of ice, continents hidden under frozen armor, and oceans sealed away from the sky by slabs of ice thick enough to swallow mountains. For a while, geologically speaking, Earth appeared stuck, as though someone had pressed a cosmic pause button. But under this silent exterior, the planet's interior paid absolutely no attention to the frozen calm above. Deep underground, the mantle moved with the same slow churn it always had. Heat rose through the crust, magma pooled in chambers and volcanoes. Those tireless storytellers of Earth's geology continued preparing their next eruptions. The ice above them muted their voices, but not their influence. Though eruptions could no longer burst freely into the open air, their gases found pathways upward, seeping through cracks in the frozen crust, or venting into the confined spaces beneath glaciers. Every volcanic sigh carried with it a familiar ingredient: carbon dioxide. In a warmer world, CO2 would have been quickly drawn into rainfall, dissolved into oceans, or weathered into minerals. But snowball Earth had halted these cycles. With the surface sealed under ice and precipitation nearly non-existent, there was no easy sink for volcanic carbon. Instead, CO2 accumulated steadily in the atmosphere, molecule by molecule, building a greenhouse blanket that grew thicker and more potent with each passing millennium. For a long time, the buildup had no obvious effect. The frozen surface reflected almost all incoming sunlight, sending warmth fleeing back into space before it could influence surface temperatures. But CO2 is persistent. It doesn't need sudden surges to shift a climate, just time. And time was something snowball Earth had in abundance. As volcanic activity continued, CO2 concentrations climbed to levels the planet had never experienced before. The atmosphere gradually transformed into a reservoir of trapped heat, capable of absorbing more infrared energy than it released. This warming did not appear as a gentle thaw, but as a subtle internal shift, a quiet accumulation of potential energy. It was as if Earth were gently raising its internal thermostat, waiting for the tipping point that would end its deep freeze. That tipping point arrived slowly, then all at once. As greenhouse gases thickened the atmosphere, the amount of trapped heat began to increase just enough to destabilize the most tenuous regions of ice. Tiny patches of meltwater formed on the surface during the planet's faint summers. Though minuscule compared to the vastness of the ice sheets, these dark pools absorbed more sunlight than ice did. Not much, but enough to create warm feedback pockets that slowly ate outward. Below the ice, meltwater carved hidden rivers, lubricating glaciers from beneath and loosening their grip on the continents. The frozen world began to stir. When melting gained momentum, it followed a trajectory Earth had no experience with, a sudden switch from frozen equilibrium to runaway warming. As open water appeared at low latitudes, the oceans transformed from reflective shields into absorbers of solar radiation. Dark surfaces drank sunlight eagerly, accelerating the melt. Glaciers that had once advanced like patient giants now retreated with surprising speed, sloughing off icebergs that drifted into newly thawed waters. The atmosphere changed with equal enthusiasm. With the ice diminishing, CO2 now had less competition from reflective surfaces, allowing warmth to accumulate more effectively. Temperatures rose at a pace that felt almost theatrical compared to the slow, icy grip of snowball Earth. In geological terms, this was a dramatic warming, swift, global, and irresistible. As continents emerged from their icy shells, rivers of meltwater poured across their surfaces, carrying sediments scraped from bedrock during the long freeze. These sediments washed into widening oceans, clouding the water with minerals that would become the foundation for new chemical cycles. Regions that had been locked in darkness for ages now gleamed under sunlight, their raw landscapes exposed for the first time in millions of years. With the retreat of ice came the revival of weather. Winds regained their vigor, sweeping across exposed land and stirring the atmosphere into motion. Evaporation increased dramatically from the newly opened seas, filling the air with moisture that began forming towering clouds. Rain returned, hesitant at first, then steady, then exuberant. Storms lashed the thawing surface, carving channels into the soft, freshly uncovered ground. The oceans transformed into vast thermal engines. Newly warmed surfaces created temperature gradients that pushed water masses into motion, reawakening currents that had lain dormant under the frozen crust. These currents circulated heat and nutrients, stirring the oceans back into biochemical activity. Marine chemistry shifted again as seawater interacted with the atmosphere, absorbing some CO2, but leaving much of it in place thanks to the overwhelming volcanic contribution. Earth, once locked in stillness, now swung toward warmth with surprising agility. The climate had never been one for minimalism. When it made a shift, it did so wholeheartedly. This global thaw also triggered a distinctive mark in the geological record: thick deposits of carbonate rock that formed rapidly in warm, mineral-rich waters after the melt. These deposits, called cap carbonates, were nature's way of recording the sudden shift from deep freeze to greenhouse warmth, layered stones that would whisper to future geologists about a planet that oscillated between extremes. Beneath the transformation lay an essential lesson in climate's long memory. The deep processes of geology, those quiet pulses of magma and gas, could override even the most dramatic surface conditions. Volcanoes, with their slow release of carbon dioxide, acted as Earth's emergency reset button, capable of steering the planet out of the coldest climates simply through patience and persistence. Snowball Earth melted not because the sun grew brighter or because life changed its habits, but because the background heartbeat of the planet, its interior heat, refused to let the surface freeze forever. Fire beneath ice had saved the climate. When the thaw was complete, Earth entered a world almost unrecognizable from its frozen past. Warm, humid, and dynamic. The climate had swung from one extreme to the other, reminding the planet, and all future life it would host, that stability was something to be earned, not given. And now, with the ice gone and heat restored, Earth stood ready for the next chapter of its atmospheric evolution. When the last sheets of snowball Earth's ice finally surrendered to warmth, the transformation that followed felt almost like a planetary exhale, a long, relieved breath after ages spent locked in frost. The world re-emerged into sunlight softened by thick greenhouse gases, and for the first time in eons, Earth slipped into a climate that could be described not as extreme, but as pleasant. Not mild exactly. The air was warm, the humidity persistent, and the atmosphere still carried a generous load of carbon dioxide. But compared to the global freeze that came before, this new chapter felt undeniably comfortable. The oceans swelled, rising over the land in broad, shallow inundations. With the weight of the ice lifted, continents rebounded slowly, their surfaces flexing upward like tired limbs recovering from long pressure. But they couldn't rise fast enough to outrun the seas. Water pooled over continental shelves, spreading into vast inland expanses that were neither quite land nor fully ocean, a network of shallow marine environments that would dominate Earth's surface for millions of years. These shallow seas were warm and sunlit, stirred by gentle tides and waves that rolled across broad platforms of rock and sediment. They were nothing like the deep, dark ocean basins of later eras. Instead, they bathed the continents in water only a few tens of meters deep in many regions, clear, calm, and rich with dissolved minerals. With light penetrating all the way to the bottom, these oceans became enormous solar collectors, absorbing sunlight and returning it to the air as slow, even heat. This contributed to the planet's new stability, a climate without dramatic seasons, without sharp temperature gradients, and without the violent contrasts that would one day drive storms on a grand scale. Humidity filled the air. Evaporation from the broad, shallow seas was constant, creating a climate where moisture drifted slowly through the atmosphere like a warm sigh. Rain fell frequently but gently, nurturing weathering on land and feeding the ever-turning cycles that connected rock, air, and water. There were no violent monsoons or dramatic hurricanes, just steady, enveloping warmth and water circulating in soft rhythms. If Earth had ever experienced something akin to a long tropical holiday, this was it. But beneath the calm surface, the oceans were busy performing one of their greatest chemical acts, the carbonate cycle. With CO2 still high in the atmosphere, seawater eagerly absorbed it, transforming part of it into bicarbonate and carbonate ions. These ions paired with calcium brought in by weathering, forming vast deposits of calcium carbonate, limestones and other carbon-rich rocks that would lock away atmospheric carbon for ages. In these shallow seas, carbonate precipitation wasn't just a geological process, it was a climate-regulating one. When greenhouse gases rose in the atmosphere, more carbon dissolved into the oceans, where it eventually settled into sediments. When volcanic activity increased CO2 input, the carbonate system buffered the changes, preventing sudden, catastrophic warming. When weathering intensified on land, nutrients washed into the sea, enhancing the removal of carbon from the atmosphere. It was the earliest version of Earth's long-term climate thermostat. Slow, steady, and surprisingly reliable. The shallow oceans acted as both participants and record keepers, turning the atmospheric fluctuations of the world into layered stone. The chemistry of seawater shifted in a dance with the atmosphere. Carbon moved between air, ocean, and rock in cycles that unfolded over millions of years, a pace that was slow but perfect for maintaining climatic stability. These oceans were not simply passive containers of water. They were engines of planetary regulation, smoothing out the wilder tendencies of the atmosphere. With so many continental shelves submerged, the sheer area available for carbonate formation was immense. Thick blankets of carbonate sediment began piling up, layer upon layer, in environments that barely experienced murky waters or turbulent waves. In this stable greenhouse environment, the world felt almost uniform. Temperature differences between the equator and poles were minimal. Warmth stretched from one horizon to the other, with remarkable consistency. Even the winds seemed to lose their urgency, drifting more than they drove, guided by gentle gradients rather than sharp contrasts. Clouds formed slowly, rain returned softly, and the climate seemed to hum along at a steady pace. This stability allowed other parts of Earth's system to experiment quietly. Weathering on land intensified not through dramatic storms, but through a constant supply of moisture and warmth. Rocks that had been exposed after the ice retreat were gradually broken down, feeding rivers with minerals and sediments. These materials found their way into the shallow seas, supporting new chemical interactions and laying the foundation for biological communities that would slowly diversify in the nutrient-rich waters. Though life remained modest and largely microbial, these calm seas offered vast, stable habitats. Stromatolites and mats of simple organisms thrived in the warm shallows, spreading across sunlit platforms and leaving their layered signatures on carbonates. The interactions between these organisms and the ocean's chemistry subtly shaped the composition of the atmosphere, reinforcing the cycles that maintained climatic balance. The world was not yet lush with complex life, but it had become hospitable, predictable, warm, and structurally diverse. Even the tectonic rhythms beneath the continents seemed to follow a more leisurely pace under this warm blanket. Volcanism continued, but its influence was tempered by the ocean's ability to absorb CO2 and convert it into rock. The climate system had, for the moment, achieved a sort of truce between internal heat and atmospheric insulation. This era was not without its hazards or inconsistencies. No geologic age truly is, but compared to the extremes that came before, it was a time of gentle equilibrium. A warm, shallow world where seas sprawled far across the continents, where carbon cycled through steady geological loops, and where the climate settled into a comfortable hum. Earth would not maintain this tranquility forever. Tectonic forces would shift continents. Biological innovations would stir new atmospheric changes, and climates would once again swing between warmth and cold. But for now, in this chapter, the planet rested contentedly beneath a greenhouse sky, wrapped in oceans that acted as guardians of stability. For the first time in a very long time, Earth felt comfortable. For millions of years, Earth basked in the gentle warmth of its shallow seas and greenhouse skies. The continents, still quiet and largely barren, waited under the sun like empty stages, vast, windswept surfaces of rock, sand, and mineral dust. Weathering sculpted them slowly, and rivers carried sediments to the seas, but life remained overwhelmingly anchored in water. The land was a silent place, bleak, exposed, and unclaimed. Then one day, geologically speaking, something remarkable happened. From the sheltered edges of tidal zones, where microbial mats clung to moist surfaces, new pioneers began creeping onto land. These weren't towering trees or lush forests. They were humble, fragile, pioneering plants. Small, simple, and astonishingly ambitious. With filament-like structures that clung to damp ground and leaves that resembled flattened, branching ribbons, they spread themselves cautiously across the margins of ancient waterways. Their arrival marked a transformation unlike anything Earth had experienced before. For the first time, life began to stitch a green film across the continents. Thin at first, but persistent. With each patch of early vegetation came a subtle shift in the atmosphere. These modest plants, quietly absorbing carbon dioxide and releasing oxygen, were about to rewrite the entire climate story in a surprisingly understated way. As land plants expanded, they brought with them a talent for chemistry that Earth had never witnessed on this scale. Through photosynthesis, they inhaled CO2 from the air, using it to build their tissues and fuel their growth. The atmosphere, which had remained stable under the guardianship of shallow seas and carbonate cycles, suddenly faced a new and enthusiastic carbon sink. Each growing stem, each spreading leaf, each tiny spore-bearing plant acted as a carbon-removing machine, soft, green, and relentless. This drawdown of CO2 didn't trigger immediate drama. The climate didn't collapse overnight, nor did temperatures plunge in a single geological season. Instead, the change unfolded gradually, almost politely. Plants simply did what they evolved to do, and in the process, they cooled the world one quiet breath at a time. Earth, without formally approving the plan, found its greenhouse atmosphere being gently remodeled. If the planet could have raised an eyebrow, it might have wondered when exactly the green newcomers had decided to take charge. After all, plants had found a way to cool the planet without asking permission. But their influence didn't stop with photosynthesis. As roots, those early pioneering structures, dug into bedrock, they altered the land in ways no previous organism had managed. Roots pried open cracks, expanded fissures, and began the slow, powerful work of breaking down rock into finer minerals. This mechanical weathering accelerated chemical weathering as well. Rainwater, enriched with organic acids produced by plant tissues and soil microbes, interacted with minerals more readily than ever before. This process had profound consequences. When rocks weather, they bind carbon dioxide through chemical reactions, sending carbon into soils and eventually into rivers and oceans, where it can settle into sediments. With plants spreading across the land, the rate of weathering increased dramatically. More weathering meant more CO2 drawn from the atmosphere and locked away in newly forming soils or carried into marine carbon reservoirs. Thus, plants didn't merely pull carbon from the air through photosynthesis. They also amplified the planet's geological capacity to remove carbon through rock breakdown. Earth's climate now had a new partner in regulation, and this partner was expanding steadily across the continents. As soils thickened, they transformed landscapes. Dusty plains became nutrient-rich patches. Rocky slopes softened into layered grounds capable of storing water. Soils themselves acted as carbon sinks, accumulating organic matter from decaying plants. Each layer of rich, dark soil represented long-term storage of atmospheric carbon, gradually cooling the climate as the green world above grew thicker. The increase in vegetation also changed how the land interacted with sunlight. Bare rock reflects light in a harsh, bright glare, but plants absorb it, using the energy to drive photosynthesis. This shift altered the planet's albedo on land surfaces, subtly changing the energy balance. More energy went into biological activity, less bounced straight back into the atmosphere. The effect wasn't dramatic in an instant, but it contributed to long-term climatic adjustments. Meanwhile, the expansion of plants transformed the water cycle. Transpiration, water released through leaves, humidified the air above vegetated regions. This shift encouraged local rainfall, creating feedback loops where plants invited the very moisture they needed to spread further inland. Rivers grew more regulated, their flow smoothed by vegetation and soil instead of rushing unimpeded across bare landscapes. This too influenced climate by reshaping where and how water moved across the continents. As greenery marched inland, the continents grew darker, softer, and more alive. Mossy carpets spread across riverbanks. Primitive vascular plants, early ancestors of ferns and club mosses, stood upright, gaining height to capture more sunlight. Their spores drifted on the wind, colonizing new ground. Each wave of expansion removed more carbon from the air, reinforcing the cooling trend. Over millions of years, Earth shifted from a greenhouse world bathed in warm, shallow seas to one where land began to assert itself as a powerful climate regulator. The drop in atmospheric CO2 was measurable in geological deposits. Carbon that once floated freely in the sky now lay quietly in soils, sediments, and plant tissues. Global temperatures responded with a gentle downward pivot, as if the entire planet were slowly leaning into a cooler, more moderated climate. Life had stepped onto land, looked around at the barren continents, and begun redecorating, not with grand gestures, but with billions of tiny green strokes. Each plant, no matter how small, helped knit a new relationship between biology and climate. The air changed, the land changed, the climate changed, and the quiet revolution was just beginning. The continents, those vast rafts of crust drifting atop Earth's mantle, have never been content to stay still. Even in the planet's earliest eras, they wandered quietly across the globe, nudged along by the deep, slow churn of tectonic forces. But by the time plants had wrapped the land in green and life in the oceans had grown more complex, the continents were ready for far grander rearrangements. Their movements, patient but unstoppable, began to reshape the entire face of the planet. And wherever the land traveled, the climate followed. For millions of years, continental blocks drifted across the ocean basins like monumental puzzle pieces seeking temporary fits. They collided, fused, fractured, and drifted apart again in cycles that spanned geologic ages. Each new configuration changed the flow of winds, the path of ocean currents, and the distribution of heat across the surface. Climate, once global and uniform in the warm, shallow seas, became increasingly regional, defined not just by sunlight or greenhouse gases, but by geography itself. The first great climatic consequence of moving continents came from the arrangement of coastlines. When continents clustered near the equator, forming wide belts of tropical land, heat accumulated along these latitudes. Sunlight poured down, warming the exposed rock and surrounding seas, giving rise to humid belts of rain and dense vegetation. When those same landmasses drifted poleward, they encountered cooler air and weaker sunlight, trading lush conditions for cold deserts and icy coasts. Geography dictated climate with surprising authority. Simply shifting a continent by a few degrees could determine whether it basked in tropical monsoons or braced against polar winds. The creation of supercontinents magnified these effects dramatically. When continental plates collided to form gigantic land masses, they altered not only the land surface but also the behavior of the oceans. A supercontinent meant long stretches of interior land far from the moderating effect of the sea. Moisture rarely reached these interior deserts, and temperature swings became harsh, scorching days, frigid nights. While coastal regions enjoyed maritime stability, the heart of a supercontinent felt climate in raw, unbuffered form. Meanwhile, the oceans responded to these rearrangements with their own transformations. Currents that once flowed freely around the globe found themselves blocked by rising land masses. Others were rerouted through narrow straits or broad channels newly opened by tectonic shifts. These oceanic conveyor belts acted as long-distance chauffeurs for heat, gathering warmth from equatorial waters and delivering it to distant coasts. When continents shifted into new positions, these conveyors rerouted, sometimes subtly, sometimes dramatically. In some eras, a wide, uninterrupted ocean girdled the equator, allowing warm water to flow effortlessly around the globe. This created a warm, world-spanning belt where tropical climates flourished from coast to coast. In other eras, blockages formed. Continents pressed together in ways that choked off these warm currents. When this happened, heat distribution faltered. Warmth pooled in some regions, while others cooled rapidly. Even without major changes to sunlight or atmospheric gases, the climate system could shift simply because continents acted like speed bumps for drifting water. Subduction zones, regions where one tectonic plate slid beneath another, became hubs of volcanic and mountain-building activity. When continents collided, mountains rose in great, slow-motion upheavals. Entire chains emerged where none had existed before, towering into the sky and casting long shadows across wind patterns. Mountains forced air upward, cooling it as it rose and triggering rainfall on one side of the range. On the other, descending air dried into parched winds that carved deserts into ancient basins. Thus, one mountain range could create lush forests on one flank and barren landscapes on the other. As ranges expanded, so did glaciation potential. High elevations captured moisture as snow, which accumulated into ice sheets. These icy fortresses reflected sunlight, cooling local climates and sometimes amplifying global patterns. Meanwhile, erosion from young mountains poured sediments into rivers, accelerating weathering and subtly influencing atmospheric chemistry over time. The planet's topography had become part of its climate machinery. When continents drifted apart, new ocean basins opened. These newborn seas invited fresh currents, carried nutrients into new regions, and reshaped temperatures along coastlines. As rifts widened, volcanic ridges formed on the ocean floor, releasing heat and minerals into the deep waters. These underwater features pushed up warm plumes that mixed with surface currents, setting the stage for new climate regimes. No longer did Earth's climate behave with the quiet uniformity of earlier ages. Instead, it developed regional personalities. Some regions experienced monsoons driven by differences in heating between land and sea. Others developed persistent arid zones, where sinking air, diverted by mountains or continental shapes, barricaded moisture from entering. Along certain coasts, cold currents suppressed rainfall and kept temperatures mild, while warm currents along other shores nurtured humid, storm-prone environments. Climate became dynamic not just because of atmospheric composition, but because continents acted as moving gates and walls in a planet-sized game of circulation. Every continental shift rearranged the pathways of wind and water, and every shift in those pathways rewrote regional climates. Earth's surface was no longer a simple, smooth sphere warmed by a uniform greenhouse sky. It had become a restless mosaic of terrains that carved, steered, and shaped climate patterns. Over millions of years, as continents continued their wandering, Earth found itself constantly readjusting. Climate was no longer simply a matter of solar energy and gases overhead. It was a living negotiation between deep tectonic rhythms and surface systems that responded to every rearrangement with new patterns of heat, moisture, and wind. The planet's geography was learning to pull the climate's strings, and climate, flexible and responsive, adapted each time the crust decided to move again. After countless rearrangements of continents and recalibrations of climate systems, Earth entered an age that seemed almost indulgent in its warmth. A chapter in which the polar regions abandoned their chilly responsibilities and embraced a climate so balmy that one could almost imagine them lounging under prehistoric sun lamps. This was the Mesozoic greenhouse world, an era when carbon dioxide soared, oceans radiated heat like gentle furnaces, and the planet's temperature gradient flattened into a near monotone of warmth. If ever there was a time when the poles forgot they were supposed to be cold, it was now. The conditions that set the stage for this warmth began deep within tectonic and volcanic processes. As continents drifted apart, rift zones opened across the crust, releasing heat and gases from the mantle. Volcanic provinces erupted with exuberance, pouring carbon dioxide into the sky at a pace that outstripped the ability of rocks and oceans to absorb it. CO2 concentrations climbed, not as brief spikes, but as elevated baselines that endured for millions of years. With such greenhouse power accumulating in the atmosphere, temperatures rose and then stayed high, tugging the entire globe into a sustained warm mode. The oceans responded with enthusiasm. Warm waters spread widely, extending far into polar latitudes. Ocean circulation became dominated by sluggish, heat-laden currents that carried warmth from one basin to another, but exchanged little cold water from the depths. Without strong temperature differences to drive vigorous mixing, the oceans stratified into layers, warm on top, cooler below, like a planet-sized thermal parfait. These upper layers acted as broad reservoirs of heat, radiating warmth back into the atmosphere and reinforcing the greenhouse state. The continents, scattered now but still influenced by earlier tectonic clustering, hosted climates that were stable, humid, and often lush. Coastlines stretched for thousands of miles, creating gentle gradients between sea and land. This allowed moisture to drift inland more easily than in later, more fragmented eras. Rainfall patterns softened, rarely delivering the violent extremes of modern monsoons. Instead, warm precipitation fell steadily across vast regions, seeping into soils and nourishing the vegetation that sprawled across floodplains and coastal lowlands. Forests expanded in this greenhouse ease. They reached high into northern and southern latitudes, growing in regions that today would lie beneath tundras or ice sheets. Giant conifers dominated many landscapes, rising like green cathedrals above ferns and cycads that carpeted the forest floor. In some regions, deciduous forests thrived in climates so mild that seasonal leaf fall was more a matter of evolutionary habit than necessity. Swamps stretched across broad river valleys, thick with sediments and vegetation. Even at high latitudes, forests flourished beneath months of dim sunlight, supported not by warmth from the sun, but by the persistent greenhouse cocoon overhead. The near absence of temperature contrast between equator and poles reshaped wind patterns. Without strong polar cold fronts to create energetic boundary zones, the atmosphere circulated in broader, slower arcs. Storms were fewer and less violent. Jet streams weakened. Climatic boundaries blurred into one another. Many areas experienced long-term climatic stability, comfortable for ecosystems, though perhaps a bit monotonous for any being hoping for a change of seasons. The animal life of this world adapted with equal enthusiasm. Dinosaurs roamed across continents that offered mild conditions year-round. Reptiles colonized high-latitude regions without fear of frost. Some species migrated seasonally, but more out of habit or access to food than to escape harsh weather. In polar regions where sunlight waned for months, animals developed strategies for low-light living rather than cold survival. The climate offered warmth even in darkness. In the seas, marine reptiles, early ammonites, and corals flourished in waters that hovered at temperatures modern tropical fish would appreciate. Coral reefs expanded across broad continental shelves, forming underwater cities of limestone and living tissue. These reef systems supported diverse ecosystems that spread from equatorial zones into regions where cold waters would dominate in later ages. The seas shimmered with life, warmed from above and below, stable in their temperature, and slow to change. Yet beneath this comfort lay vulnerability. The stability of a greenhouse world depended heavily on maintaining high carbon dioxide levels and warm oceans. The climate was resilient to small disturbances, but sensitive to major disruptions, particularly those involving changes in volcanic output or the positioning of continents. With ocean mixing sluggish, the deep waters accumulated carbon and nutrients without easy release. Organic matter buried in sediments could suddenly alter atmospheric chemistry if tectonic events exposed it. And while warmth allowed life to flourish broadly, it also meant ecosystems grew tightly tuned to temperature stability. Subtle cooling could trigger contractions in tropical and subtropical habitats. Shifts in rainfall patterns could transform forests into semi-arid plains. The very lack of strong temperature gradients meant that any deviation in the climate system, once started, had trouble finding equilibrium. This greenhouse paradise, so gentle and stable on the surface, carried within it the quiet fragility of a system held aloft by carefully balanced processes. Still, for millions of years, the Mesozoic climate thrived as one of Earth's great warm epochs. Forest canopies stretched from equator to polar circles, seas shimmered with unbroken warmth, and the atmosphere embraced the planet in a luxurious greenhouse blanket. Heat flowed gently around the globe, not racing from equator to poles, but drifting lazily across continents and seas. The poles, basking in their unprecedented warmth, lingered in their forgetting, unaware that in future ages they would be called back to their icy duties. For now, the Earth remained lavishly warm, wrapped in a climate that encouraged life to spread far and wide. The age of extremes was not extreme because of cold or heat alone, but because the planet dared to sustain uniform warmth across its entire surface, an experiment in global comfort that could not last forever. After the long, luxuriant warmth of the Mesozoic greenhouse world, Earth began a new chapter marked not by dramatic upheaval, but by subtle change, a steady, careful, almost contemplative shift toward cooler times. Unlike earlier climate swings, which often arrived with theatrical suddenness, this cooling unfolded at a patient geological tempo. It was as if the planet were tapping its toe experimentally on the threshold of cold before deciding, yes, perhaps it's time to bring ice back into fashion. The roots of this cooling lay deep in the slow choreography of tectonic plates. Continents once clustered in warm configurations moved steadily into positions that disrupted the planet's heat distribution. Land masses drifted closer to the poles, providing stable platforms where winter cold could accumulate instead of being dissipated by warm seas. Islands and coastlines gradually rose from the ocean, narrowing passages through which heat-bearing currents once flowed freely. These shifts nudged Earth toward a new atmospheric balance, one that favored the gradual return of chill. Meanwhile, mountain building surged across the planet. As continents collided and crust thickened, new ranges pushed skyward, jagged, towering chains of rock that pierced the wind. These rising mountains did more than sculpt landscapes. They altered the chemistry of the air. Exposed to weathering, the fresh rock surfaces reacted with carbon dioxide carried by rainfall and groundwater. Each reaction locked away a tiny amount of CO2 into minerals, removing it from the atmosphere grain by grain, drop by drop. Over millions of years, this mountain-driven weathering acted like a quiet siphon, drawing down CO2 levels, and with less carbon dioxide in the air, the greenhouse effect weakened. The cooling influence of these mountains didn't stop there. Their sheer bulk rerouted atmospheric currents. Air was forced upward along steep slopes, cooling and shedding moisture as rain or snow. The leeward sides of these ranges dried into rain shadows, creating regions where aridity increased and vegetation retreated. This reorganization of moisture shaped new climate zones, dividing once stable environments into wetter and drier districts. Such shifts told the atmosphere where to deliver its warmth and where to withhold it. As the continents drifted, oceans adjusted their own participation in the cooling. Warm tropical waters that once flowed unimpeded toward the poles found their routes restricted by emerging land bridges and narrowing straits. When ocean currents are forced into new paths, their role in transporting heat changes dramatically. Regions that had once basked under warm currents found themselves exposed to cooler waters welling from the depths. Coastal climates moderated, then cooled. The Earth was no longer the smoothly warmed sphere of the greenhouse age. It had begun developing thermal contrasts again. At high latitudes, winter grew more persistent. Summers lost a sliver of their strength. Snow lingered a little longer each year, reflecting sunlight back into space. In the beginning, these snows melted eventually, a kind of seasonal rehearsal for a climatic shift that had not yet committed to permanence. But the cooling trend continued. Each year, the ice lasted a little longer. Each century, it crept slightly farther from the poles. It accumulated quietly, without fanfare, until, finally, it stopped melting entirely in some places. This was the first reappearance of polar ice after tens of millions of years. Not vast sheets yet, not the sprawling frozen continents of future ages, but footholds, small, stubborn pockets of persistent ice that clung to high-latitude coasts and sheltered peaks. They formed as part of a gradual climatic rebalancing, proof that the cooling had grown real enough to shape the cryosphere once again. Ice, once it gains a foothold, has a way of encouraging more of itself. These early glacial patches reflected more sunlight than the dark soils and forests they replaced, subtly cooling their surroundings. Their presence signaled the beginning of a long-term positive feedback loop, not an abrupt plunge into global freeze, but a slow invitation for more ice to form. The planet wasn't rushing. It was adjusting, step by careful step. During this cooling, life continued its usual inventiveness. Forests migrated equatorward as climates shifted. Some regions became temperate rather than tropical, while others transitioned into drier grasslands or semi-arid expanses. Fauna adapted, evolving traits suited to cooler conditions or relocating to climates that preserved the warmth they preferred. No sudden extinctions marked this transition, just a slow reshuffling of ecosystems, a quiet realignment of biomes responding to the planet's changing mood. Ocean chemistry changed as temperatures declined. Cooler waters hold more dissolved gases, and the oceans absorbed both oxygen and carbon dioxide differently than they had under greenhouse warmth. These shifts subtly altered marine habitats, influencing where nutrients upwelled, which species thrived, and how food webs arranged themselves. Coral reefs, long accustomed to warmth, retreated from some regions while flourishing in others. The seas did not collapse into crisis. They restructured themselves with calm persistence. The atmosphere, too, developed new behaviors. With less CO2 trapping heat, the planet shed more thermal energy into space. Seasonal cycles strengthened. Temperature contrasts between equator and pole sharpened for the first time in ages, rekindling atmospheric circulation patterns that had lain dormant during the greenhouse lull. Winds picked up, jet streams strengthened, and storms gained new shapes, still modest compared to later Ice Age tempests, but lively enough to reflect a climate awakening to its cooler identity. All of this cooling unfolded not as a catastrophe, but as a long-term drift, a gentle slide, almost meditative in its pacing. Earth shifted from an age of warmth into an age of moderation, its climate learning patience once again. Ice, after its extended absence, returned tentatively, as if checking whether the world was ready for it. Over millions of years, the answer became clear. The planet was indeed growing receptive to cold. Ice did not yet dominate, but it had resumed its ancient role as a shaper of climate, marking the beginning of a transition that would echo into later chapters. The long cooling had begun, not with drama, but with quiet certainty. As Earth continued its slow drift into cooler climates, a new pattern began to dominate its behavior, one not dictated by the arrangement of continents, nor by volcanic ambitions, nor by sudden atmospheric overhauls. Instead, the planet began to follow a rhythm set by celestial geometry. It was as though Earth, having experimented with fiery extremes and greenhouse gentleness, now settled into a cosmic waltz with the sun, guided by the subtle pull of gravity and the quiet precision of orbital mechanics. These rhythms, later to be named Milankovitch cycles, were not loud proclamations of change. They were soft nudges, slight adjustments in how the planet tilted, rotated, and revolved. But subtle does not mean small. Over tens of thousands of years, these small shifts in Earth's orbital dance orchestrated massive swings between icy expanses and warmer interludes. The planet's climate began to pulse. Inhale cold, exhale warmth, in a cadence that would shape landscapes, oceans, and life for millions of years. It started with the tilt. Earth's axis is not fixed. It wobbles gently over time, tilting more steeply or less so in cycles lasting around 41,000 years. When the tilt increased, sunlight reached higher latitudes more directly, softening winters and granting summers enough warmth to melt accumulated snow. When the tilt decreased, sunlight struck the poles at shallower angles, allowing winter's breath to settle deeply and summer's warmth to retreat. Snow lingered, ice thickened, a quiet invitation for glaciation formed. Then came the eccentricity of Earth's orbit, a slow stretching and smoothing of the orbital path around the sun. Over cycles lasting roughly 100,000 years, the orbit oscillated between more circular and more elliptical shapes. When the orbit elongated, Earth spent part of its year farther from the sun, receiving slightly less solar energy. These shifts alone could not freeze the world, but they amplified the effects of axial tilt. The cooling deepened. Ice sheets grew bolder. And woven through these cycles was the precession, the slow turning of Earth's rotational axis, like a spinning top tracing circles in the air. This cycle, unfolding over 23,000 years, determined when each hemisphere faced the sun at different points in Earth's orbit. It shifted the seasons subtly, influencing whether summers arrived when Earth was closer to or farther from the sun. A seemingly small timing issue, yes, but in a climate system sensitive to the balance of melting and accumulation, timing was everything. Together, these orbital rhythms shaped Earth's new climatic personality. Winters in the higher latitudes became sometimes fierce, sometimes mild, depending on how the cycles aligned. Summers alternated between powerful enough to erase winter's work, or too gentle to chase away lingering snow. When a sequence of orbital configurations favored cooler summers, snow began to accumulate year after year, compacting into firmer layers. Over time, small patches of ice grew into persistent fields. Fields became sheets. Sheets spread outward into the great ice masses that carved valleys, sculpted plains, and transformed continents. The pulse of glaciation was slow but deliberate. Ice did not rush. It crept, advancing with the patience only geological processes possess. As ice sheets grew, they reflected sunlight with dazzling efficiency, reinforcing the cooling trend. The northern hemisphere, with its abundant land masses, hosted the largest of these frozen expansions. Continental interiors found themselves gripped by kilometers of ice, their landscapes hidden beneath frozen plateaus. But the pulse did not freeze Earth indefinitely. As orbital cycles shifted again, summers strengthened. Snowmelt outpaced snow accumulation. Ice sheets thinned, cracked, and retreated. Their withdrawal was equally transformative. As glaciers melted, they released vast volumes of fresh water into the oceans, raising sea levels and reshaping coastlines. Rivers swollen with glacial melt carved deep valleys. Lakes formed where blocks of stranded ice melted away. The climate warmed, not in a sudden burst, but in a slow, determined inhale that followed the long exhale of glacial cold. These transitions were not isolated events. They repeated over and over in cycles lasting tens of thousands of years. The planet developed a dependable rhythm: glacial advance, glacial retreat, advance again, retreat again. Climate became a system governed partly by celestial timing, responding with remarkable fidelity to shifts in Earth's position relative to the Sun. It was as though the planet had learned to breathe in time with its orbit. During glacial phases, colder, drier climates dominated many regions. Deserts expanded. Winds grew stronger. Dust traveled across continents and oceans, delivering nutrients to distant seas. In interglacial phases, warmth softened the world. Forests migrated poleward. Rain returned to places once parched. Lakes blossomed in basins previously emptied by the cold. Each cycle redrew the map of biomes, offering new habitats and shrinking others. Life adapted to these shifting environments with its characteristic resilience. Some species migrated with changing climates. Others evolved new strategies to endure cold or exploit warmth. The waxing and waning of ice shaped not just the land, but the evolutionary pathways of the organisms living upon it. Through all these changes, nothing in the climate system operated independently. Ice, sunlight, atmosphere, oceans, and orbital mechanics intertwined in an intricate web of cause and effect. A subtle wobble in axial tilt could influence rainfall thousands of miles away. A small change in Earth's distance from the Sun could determine whether an ice sheet advanced into temperate latitudes or retreated toward the Arctic. The glacial-interglacial cycles became one of Earth's most elegant forms of climatic orderliness. A planetary heartbeat measured not in seconds, but in millennia. A rhythm steady enough to be predictable, powerful enough to sculpt continents, yet gentle enough that life continued to flourish through the cycles. And so Earth breathed, slowly, deeply, in long cycles of cold and warmth, guided by the geometry of its orbit and the unwavering pull of the Sun. As Earth emerged from the long sway of glacial rhythms, the planet found itself in a state that could best be described as dynamic equilibrium, balanced, but only in the way a dancer remains upright by constantly shifting their weight. For all its cycles, upheavals, warm ages, and icy interludes, Earth had not been moving toward a final, stable climate. Instead, it had spent billions of years refining its ability to change, to negotiate, and to adjust. Climate was not a finish line. It was an ongoing conversation between the deepest layers of the mantle and the highest reaches of the atmosphere, each speaking in their own slow dialects of heat, motion, and chemistry. By this stage in Earth's story, the planet had an impressive collection of climate-shaping tools: continents drifting on tectonic rafts, oceans circulating warmth and cold in looping conveyor belts, an atmosphere that responded to subtle shifts in composition, and a biosphere intimately woven into the machinery of carbon and oxygen. All of these systems, rock, water, air, and life, cooperated and competed in a long-standing interplay that made climate neither static nor chaotic, but something more intricate, restless, yet purposeful. The Sun, too, played its quiet part. Its energy output continued to grow slowly over geological time, brightening by small increments that accumulated across eons. This gradual luminosity increase nudged Earth's climate, warming it here, challenging it there, forcing the atmosphere and oceans to absorb, reflect, or redistribute energy in ever-evolving patterns. Meanwhile, Earth's orbit kept time in cycles, ensuring that cold phases and warm interludes alternated like the verses of a cosmic poem. The planet's relationship with the Sun had matured into a subtle balance of distance, tilt, and timing, a dance choreographed by gravitational pulls and orbital mechanics. Life, never content to sit quietly in the corner, continued to influence this balance in ways both gentle and profound. Plants drew carbon dioxide from the air, altering the greenhouse effect. Microbes in soils and oceans mediated chemical reactions that shaped atmospheric gases. Animals transported nutrients across landscapes, subtly shifting ecological and climatic interactions. And ecosystems responded collectively to climate changes by expanding, contracting, and reorganizing themselves with remarkable resilience. Every organism, no matter how small, contributed a tiny voice to Earth's climatic dialogue, sometimes harmonious, sometimes disruptive, but always influential. With so many interconnected pieces, Earth's climate became a tapestry woven from feedback loops. Some were stabilizing, pulling the system back toward moderation whenever it drifted too far. Others were amplifying, allowing small changes to blossom into major transformations. The challenge and triumph of the climate system was in how these feedbacks combined. A volcanic eruption might spew cooling ash into the sky, but also release warming gases. A rise in temperature could melt ice, lowering reflectivity and deepening the warmth, yet also invigorate weathering processes that would eventually draw carbon dioxide from the air. There was no master controller, no single process in charge. Climate was a mosaic of influences working together, adjusting endlessly in response to internal changes and external nudges. This made it inherently flexible, capable of recovering from asteroid impacts, massive volcanic outbursts, and biological revolutions. But it also meant climate was never completely at rest. It could be steady for millions of years, only to shift again when tectonic plates rearranged or a new evolutionary innovation appeared. The oceans embodied this restlessness perhaps better than any other system. Their vast depths stored heat like ancient memory, releasing it in slow pulses that influenced weather patterns and coastal climates. Surface waters responded to winds and sunlight, while deep waters carried nutrients and carbon along global pathways that took centuries to complete. The oceans served as both stabilizers and instigators, holding the climate steady during some eras and leading it into new regimes during others. Each wave, each current, each upwelling was part of a much larger rhythm that had begun billions of years earlier. Meanwhile, the atmosphere, light, thin, and endlessly mobile, reacted to every shift in land, sea, and life. It carried heat from warm regions to cold ones, moisture from oceans to continents, dust from deserts to forests. In its movements, it stitched together the climate system, ensuring that no region of Earth remained isolated from the influence of another. The atmosphere was the messenger between systems, delivering their interactions across the globe. In this great, interconnected web, climate became something more than a set of temperatures or patterns. It became an emergent property, a story told by the entire planet working together. A story not of stillness, but of motion, not of stability, but of adaptability. As Earth continued its long journey around the sun, the climate never reached a point of finality. How could it? When continents continued to drift, when the biosphere continued to innovate, when the sun continued to brighten, when ice sheets advanced and retreated like slow, deliberate breaths. Climate was not aiming for perfection. It was maintaining balance through change. And that is the legacy of Earth's climate, a restless balance shaped by physics, sculpted by geology, and guided by life. A balance flexible enough to endure extremes and stable enough to foster complexity. A balance that reflects the planet's ability to adapt, evolve, and carry on through billions of years of transformation. If Earth had a sense of humor, and perhaps it does, tucked somewhere in the shifting winds, it might say that its climate never truly settled down. It just learned how to keep going.